guys ready?
Yeah.
Okay. Okay, all I did was I was just trying to do the optical angle of why we see what we do with Blackpool and why Blackpool Tower is optically actually just larger than the mountain in the rear view, and why you can't really scale it to get the same phenomena. Okay, so I started off with the observer elevation and angle to the observation. The observer's elevation and angle towards observation is highly important, as it will determine many factors on what you will be observing in the distance. The elevation is the altitude angle. That's, to me, that is the most important factor when it comes to doing an observation, because your angle changes what the observation will be. That's where this photo is here. You can see the camera pointing down, how it's changed the relationship between how it was sitting level and when it's pointing up. I'm gonna have a video playing next that we can watch that will give a more idea of what I'm explaining here. Okay, so I'm just gonna play this video. Look at the lines on the poles. All I'm doing is I'm just changing my elevation angle, nothing else. Okay, before I go through to the next slide, I just want to ask, what did you guys all see with this video?
Are we looking at the yellow lines on the pole, yeah?
Yeah, I can play it again if you want to see it.
Yeah, go on. Keep it playing.
But look carefully, but don't just look at the lines. Look at the whole surrounding. Look at that hydraulic pump. Look at the shade net in the back.
So the lines in relation to the background as well, yeah?
Yeah, oh, sorry, I just want to go back. Okay, yeah, look at everything. Okay, I'm going to play the video again.
Nice, you made them all disappear into the bottom one.
Yeah, what did you see between the three lines though? Did you see how they were changing positions?
Yeah.
In relationship to each other, yeah.
Yeah,
Mhm.
the further one has more parallax compared to the closer one. When you're moving down in elevation, the further one seems to be dipping down much quicker than the one closer to you. And when you're level to it, the three are relative to each other. I can want to go to the next slide, then I can explain it better. Yeah, I took the still shots where it's showing the higher elevation, the level, and the lower. How you can put them and you can see them towards each other with the difference. This very simple demonstration saying the same distance at just adjusting the elevation shows how the angle changes everything to the observation. When observing from a high elevation altitude, the angle widens and pushes the limit further. That limit I'm talking about is literally just the limited angle from the deck. I'll get to that later on when we're talking about that. When you're with a level angle in a sort of tunnel to the convergence, that's when you're level, and it's the same effect as when you're standing in a hallway. You have that tunnel effect, the convergence to the same point. Because you're level, everything in observation is going to the same convergence at about the same rate. But the floor's angle is still the biggest one. So thus you'll still have bottom obstruction quicker with distance. So when you're at lower, the angle closer to the rises and the closest to the gap to the limited angle in the distance. This is why you get dropping down effect. The things to notice: at the low elevation altitude, the car shade net sinks behind the hydraulic pump, and thus the pump occults the shade net. The ground lifted as you observed lower the elevation altitude. So can you see the first photo to the last photo, how the shade net that's further than everything else dropped behind the hydraulic pump. Then the hydraulic pump was occulting the shade net.
Yeah.
Any questions?
Nope.
Because I think that's quite straightforward.
Yeah, I'd say next time you do those lines,
Yeah.
if you level off the ones at the high one and level off the ones in the middle and level off the ones in the bottom, then you'll see the relationship of each set of lines with the last ones, because they will all be in line at some point.
Yeah, that's what I was trying to show when you level.
Yeah.
The middle one was the level one. You could see they all stayed level together. As soon as you went lower in elevation, the back one dropped lower, and the one closest to you went higher. So it has an opposite reaction when you're going higher. Then the back one lifts up, and the front one drops down.
Yeah.
Yeah, this is me taking all 3 photos with the different elevations and just aligning them to the bottom of the wheel where the hydraulic pump wheel starts on the ground. Look at the compression size just with that little elevation. How from the higher to the level to the lower, how much that hydraulic pump has compressed downwards. And I mean, this is at a short distance.
I've lost the picture. I did click on the full screen thing, and I've got a spinny.
No, we can wait. It's fine.
Yeah, it happened to me a minute ago, Bevan. It actually, it just took a minute. That was all.
Yeah, I think Discord's being a bit
iffy.
Yeah.
No, it's fine. We'll wait till you guys come right there.
Yeah, I was thinking I did this with a level on my board, and I had the water level and the auto level, the spirit level, and they were only about 4 or 5 inches apart. But just moving the camera from one to the other made a drastic change over what you saw as the one that, obviously knowing that they are both level. But just changing the angle of height, or the height of your thing, the relationship of level looks different when you're looking at it from another level.
Yeah, that's why elevation angle is very, very important when you're making observations, which I think people take highly for granted. They just try and say, okay, I see eye level, but they don't see where's the focus point of that eye level. Is it lower than that object, or is it higher than that object? And that can give the effect of it sinking or rising, according to the view. Is it showing now by you guys?
No.
I've just dropped a screenshot in the live chat.
Of what?
Of what we're looking at, the picture that Flatsoid, the compression on the, what is it, Flatsoid?
Yeah. Compression due to the angle.
Yeah, but what is it, the yellow thing we're actually looking at? What is it?
That's the hydraulic pump.
Uh-huh.
You see that bottom red line? I aligned all 3 of them to the wheel on the floor. And if you look at the lines, you can see it gradually compressing more and more until you finally get to the top line. See how different the lower elevation has compressed much more compared to what it was on the higher.
The low elevation is the one on the right, yeah?
On the right, yeah. And then the level is the middle, and the high is the left. And you can see that it's actually shortened, it's compressed the actual whole thing just because of the elevation. Yeah. So the hydraulic pump, when aligned to one another, the compression is more noticeable. The elevation altitude has a major impact on the compression. The distant object has more of a compression effect, the angular size never changed from left to right, only from top to bottom. This is also one important fact I wanted to make to the people. They think the angular size would change top, bottom, left, right all the time. No. When you change your elevation angle, it also changes angular size because it compresses. That's why these angular size calculators don't take perspective into account. That's literally just what it would say. That the angular size would be at that distance, but it doesn't take your observation angle, your elevation angle towards the observation, and that's what throws everything out of whack. Okay, I'm going to go to the next slide if that's fine with you guys.
Mm-hmm.
Okay, yeah, I was just doing an orthographic representation with the Blackpool Tower and the mountains in the back.
What I needed. Just you switching to the next slide.
Okay.
Yeah, I'm back.
Okay. Yeah, I'm just trying to show the orthographic representation and to show why orthographic representation does not depict reality. You see, what I'm trying to show you is just forced perspective, actually. That's why you see the tent. The tent is not as big as the mountain. It's literally just a coating over that further mountain because it's closer to you and the angled view. If that person had to put the camera on the floor to watch that tent, it's going to be higher than the mountain. Just like that hand holding the Eiffel Tower, the hand's much closer in front of the camera view and the guy holding the sun. That's all it is. There's the forced perspective equation if everybody wants to go and work it out. This is what the radians worked out to, and the angular size. You see the angular size still shows bigger on the mountain in the background, but as I said, there's no angular observation angle taken into account. So you can't really justify it from a picture to say it will be higher or lower. Now I'm showing it again with orthographic representations. They do not depict reality. The reason for that is because it just takes it as a single triangulation angle from the ground. There's no perspective taken into account. The bottom one, it's also not reality, but it's sort of a perspective orthographic representation because it takes two angles. It will take the deck and the top. If you take it into relation, you see the mountain, according to the angle with the Blackpool Tower, would have the peaks would look lower, just because the bottom is also now under the surface deck, according to that level of the eye observer. Did that make sense?
The the graphics were a bit iffy at the beginning, but yeah, I can read it now.
Okay. So you understand, the top one is normal triangulation. You're literally only taking a single angle.
Yeah.
So the top of the mountain shows higher. There's more to see.
That would be the trigonometrical view that people keep using, the right angle triangle.
Yeah, exactly.
And the other one is more of a isosceles.
Yeah, it's more of a perspective based. It's more of the ones that you would use in surveying.
Yeah.
Because it takes some errors into account.
That's a true optical representation, the bottom view, whereas the top view is a geometric.
Yeah. Okay, then we see this is the picture, then we just say, okay, what do you see here? This is me trying to just make a visual to say, okay, what we observe is compression of the mountains in the far distance, that we've explained. We observe the occultation of Blackpool that is closer to the observer, obviously because the Blackpool Tower is closer and is close to the eye level, it's going to occult over the much further distance mountain in the background. We observe that due to the viewing angle, the tower has a larger angle towards the eye level. which is what I was saying. When you change your elevation, you actually decreasing the further observation angle. So that mountain, when you change your elevation, you're actually changing its angular size. It's not staying that angular size, and that's why when they use the trigonometry, it does not actually depict reality. They're keeping it to a set value. It's just straight. It doesn't take observation angle into account. So that cancels out the drop effect that you would get with far distance observations, like we saw with the pole. When I changed the elevation, how it changed the back observation to drop more. Yeah, I was just showing the apparent size change at a distance.
That's bad graphics. I can't make much out there. I don't know what anything's going out through to it. What's everybody else like? Is it just me that's getting a bad?
A little fuzzy.
Can you?
Unless we wait a bit till it loads up properly.
Yeah. How's it doing for everyone else, or is it just me?
No, it's not loading.
Yeah, no.
It's the writing.
Yeah.
It's Discord. Well,
Yeah.
Bev, if you...
Have you got slides? Can we?
I can send you the slides.
It's not a dodgy photocopy, is it? What you showing us?
No.
Yeah.
Must it take a 2-minute interval that I can send you all the slides? Then if we go through it, you can put it up
if
on
you
screen
can just put them into the live stream.
Okay.
And you tell me which one I'm clicking on, and we'll just click on them, together in the live chat.
Okay. Okay, I might just have to take screenshots and stick it in. Okay, I'm just going to stop sharing quickly so I can...
Hold on, no, it's right now. Literally.
But then as I clicked out, it's like, whoa, that looks great.
Oh no, my phone's freezing.
Yeah, it did say your phone's running low on battery. Are you plugged in?
Yeah, I think I'm gonna quickly plug it in. Okay, can you see it now?
What's that look like?
It's okay, but I think it's not perfect.
Yeah.
For some reason, it's slightly blurry to me. I'll put my glasses on. Maybe that's it.
I've just got blue squares going round
Me
and
too.
round.
Me too. I think
Dance.
probably, if these are just slides,
Dancing.
it'd be easier if you just
Yeah,
pop
yeah,
them
Okay,
in there.
okay, I'm gonna send the slides to you quickly.
Yeah, nice one.
Just gonna quickly send it to you. I'll be back on now.
I did that. I went
'Cause
to
now
go and have a
to-
look at the
okay.
optics. And
Quickly taking those screenshots.
it's dead geometrical, sort of the way all of those.
But it's making sense so far.
The figure
Like I said, guys.
contained by a set of visual rays is a cone of which the vertex is at the eye and the base at the surface of the object seen. And that's so elegantly put. And I highlighted that one. That things seen by higher visual rays appear higher, and things seen by lower visual rays appear lower. And that
Okay, I'll send-
things seen under more angles are seen more clearly. If you go up higher, you can see better.
Yes, because you're opening your field of view.
Yeah.
You're pushing out your limited angle further.
Seen
And
that
that's where you can
thing
see
seen
better.
under more angles. You just see more of the angle of it. That not such a narrow angle.
Yeah. Exactly. You're not you're just push in that everything that's compressed into that small little area is just being pushed out further.
That's another one as well. That thing seen under a larger angle appear larger. Those under a smaller angle appear smaller.
I would say that's a bit like looking up at the sky.
Mm-hmm.
At the stars without any limited angle, apart from your own eye.
Yeah. How big's the sky?
Ah.
Massive, isn't it?
Okay, I see them mixed it up now.
Okay.
Ready?
Well, you tell us which one you want.
Okay, go to the second last one.
Apparent size change. Yeah.
Apparent size change, yeah, at a distance. Okay, you can see it perfect now.
Yes.
Okay. This is just me trying to show the image becomes inversely proportional to the distance away. So this means if we double the distance, the object size will be reduced by about half, and so on. This is just a simple equation to show the height is inversely proportional to the object over distance. If you wanted to do it to a ratio, you got your height 1, which would be over the height 2 equals to the distance 2 over distance 1. It's just a quick ratio calculation that anybody can work out. And then I've put the orthographic representation there, showing with each meter how it changes angular size, and the perspective representation, if you stand in front of it, how it's looking to go down into the distance. So this is a 32 centimeter roll, and the first pictures on the left is I'm standing a meter away from the distance. My phone is sitting exactly the same elevation, everything on the ground. The second one is 2 meters away, and the third one is 3 meters away, just to show how it changes angular size as you move away. The thing you must notice is the ground is raising towards the convergence line, and those grey lines are lowering towards the convergence line as you go away with distance. So that is about it. So I would say, yeah, and just the interesting fact, the limiting point for your eye is around 1 arc minute, which is strangely enough, if you take it to the Rayleigh criterion, 1.22, which is about the same as what the Earth curve calculators push the horizon to from a observer's height. Just interesting.
I think we had a representation of a 1 arc minute, and I think that was around 900 meters away, was it? I think it was around 900 meters. An average soccer football would be the angle that you saw that football at would be a minute. I think it was, may have been 400 meters or something, maybe 420 meters. I'll have to check it up on that, but that's about how much a 1 minute of angle is from the horizontal. Is the like a football over 400 meters, I think, if you take that. Yeah,
and that changes with your elevation, which is very interesting.
Can I point out the H and the D are the only things in there, and that H would be a vertical, a right line,
yes,
and the D would be a horizontal, right? A horizontal distance and a vertical height.
Exactly, no curves at all. Horizontal plane with a vertical.
No angles needed, just the relationship of two of the sides of a right angled triangle. A direct proportionality between the two as well.
Yeah. If you're ready, we can go to the next slide. It's the last one.
Why we see Blackpool Tower.
Yeah.
Yep.
Why we see Blackpool Tower higher than Dow Craig.
Yep, we're on it.
Okay. The observer's eye line is looking upwards at Blackpool at the limiting angle, and that rises to eye level. Perceived eyesight to the mountain is obscured by Blackpool, aka optical occultation. Though according to angular size trigonometry, Blackpool Tower should be smaller. This calculation does not take perspective into account or even any optical phenomena associated with distance. The convergence compression is simply seen through distance from observer's angle. The angle changes what you will see and what you observe. The observation angle is the reason by doing small scale it does not fit to reality. This does not take into account the aperture and the observation angle. Matter of fact, you can cancel out a considerable effect of compression. The compression is always more expressed with the further distances, as the limited angles are much more closer to one another, hence diffraction limit, and why you have bottom-up obstruction. So what I'm trying to explain here is you can't really take this and do a to-scale demonstration exactly what you need. I'm going to be showing you a scaled version, which Bearded Devil did really great. I really applaud him for it because I asked him to do it. He did it as I asked. But there's one thing he didn't take into account, and that's my whole argument. The observation angle. By taking to scale, it's just too small. You would never be able to mimic the actual observation with that distance. The thing is, the camera itself would have to be about 2 millimeters off the ground, and the aperture of his camera is too large to actually mimic what the size of the aperture would be on that camera with that distance in actual reality. So what I'm trying to say is you can try scale as much down as you want. The more you scale it down, the less of the reality of the distant actual observation you'd be able to actually mimic, because you have to scale every single aspect down, not just the mountains and the distance. Does that make sense?
Yeah, it's like that line that you put in across as an eye line. Is it's hard to get graphically what you actually see, isn't it? It's hard to represent it on a 2D thing, because what you do see in reality is has an incline that when you look at it and try and put it on paper, it's nearly at 30 degrees, isn't it?
Yeah.
When you look at an isometric drawing, and that's the 60 30 90 triangle, I think that's the most graphic representation of it. So
yeah, I think it points it out quite well.
Yeah. Does
But
everyone
yeah,
else get that? Or is it like we're speaking a different language, or is it something you just need to get your head around? It's hard work trying to express this in words, isn't it? when the moment you start trying to look into the minutiae of all of these things, and you realise how little you can actually explain yourself.
Yeah, it seems simpler, but the more you look at it, kind of like, it's distorted sometimes, the logic coming from it. What was I gonna say? So you get 90. So you put like say from the observer, you put just a straight vertical above the observer, and then you do a horizontal 90. So you're seeing the angles from say 30, 60, 90. So the 90 you would never, obviously, when you're looking up, right? That's looking up, and then. But you never do that. But the tower, the top of the tower, you would say would be what angle? Like is there a certain angle, or is from the picture that you're seeing? Would that be like a 60 or a 30? Because it's hard to see because
the 90 will always be the vertical height of whatever at the other end of the triangle. Now,
so that's
what you see. You can see it visually lifts. So drawing that baseline with a 90 degree like they do when they do trigonometry, and they then proportion it and go, this doesn't look right, and it's like, well, it doesn't look right because it's not how you actually see. The optics of the eye and the visual representation of this has an upward lift to it. doesn't actually have an upward lift to it. Doesn't even have a downward curve afterwards.
Yeah,
You know,
it's hard
like
to have a
just-
baseline.
Yeah.
It's they're trying to base geometry off of optical effects due to the perspective angle, and you can't really base it off of a picture because the angle is just too tight. It's as simple as that.
Because the baseline from the eye level, that would be your 0. I'm thinking, but then when you put the angle, say a 90, from your eye height or your observer height, whichever one you use, I guess. But a lot of times you're just looking through the optics of your eyes, so it's you're basically using your eye as the base, sort of as the 0 point. But it's like you were saying, I think it's hard to establish that because you're using optics, yeah.
Yeah, because you have a focus point, and just your relationship to the focus point changes the whole observation.
Yeah. Yeah, there's an old set of geometry books that cost like £1,000, and they have perspective and all that. That's part of the geometry study for when they were doing big hallways and tiling and stuff like that. It was all figured in, so they did have an art to this. There was a way to describe it in the past, and obviously it's been lost for a reason. And having to reorder your brain into how to look at things to not get fooled.
Yeah. Are you ready for the next slide?
Yep.
It's I think the first one that I put in, the limit to angle rises, the one that says not curve.
No curve. Yeah, not curve. Yep, got it on.
Okay. This is just a depiction of showing the largest angle is always the ground as we stand on it. As you rise in altitude or elevation, it changes and pushes the limit angle out further. That's actually all we've been saying the whole time. So it's just they take this limited angle, which they see as the horizon, and call it Earth curve. It's literally just the limited angle due to the observer's angle, observation angle, which is compressed into the diffraction limit. So that point where the limit of the viewing point due to the angle is compressed and becomes 1. That is now the larger angle which occults in front of the furthest smaller angle, and that's why they see it as curve. But it's just you magnifying the limited angle due to your observation angle. Make sense?
I think, isn't there like a part of a mirroring that takes effect along that line as well? That's what builds it up. I've got, like I say, when we went to Bedford Levels, there's a tiny ripple in the water that you can see sort of waves in it, and there's mirror before it and mirror after it. So there's just like a little break. I know what you mean though, that one line in the middle. It's
and because the horizon rises to the convergence point, which rises to eye level, it blocks it out quicker towards you. So that's also what creates the horizon line.
Yeah, well,
and why you can have the red effect.
Line?
Well, I'm just saying it would be what they call the horizon line for the Earth curve, because they wrongly associate it as the Earth curve blocking something in the distance, which it's literally just the raised limited angle towards the viewer's deck. And that's why it's possible to see a mirror, because it's a flat horizontal deck.
Yeah, see that bit before it isn't water, that is the mirror, and then you've got that bit the edge, and then that steps away as you change. more studies needed on it, but it gives us a new idea. I think I seen one. Travis had a video the other day and put it in Brandon's that has a similar sort of thing, and it shows that break in the high band there that you're talking about. I like it.
Okay, and then I just got the second photos of just the limited angle rises, just what we've just been talking about now.
Yep, we're on it.
Yeah, so that's just there where I'm trying to explain the limited angle rises to your eye level. That's what gives you the apparent horizon because of that limited angle. And then the picture just underneath it, this is Bearded Devil's demonstration.
Just a thank you, yeah.
The one.
Yeah.
Just a thank you for Bearded Devil. Yeah, it's got the measurements in. You can see it, correct?
Just a thank you from Bearded Devil. Yeah, thank you to Bearded Devil. Yeah. That's
okay. Yeah, what do we observe here? Well, what would you expect when you see observer angle looking straight ahead on the tower? If you look at the eye level from the camera, this is what I was trying to explain earlier. It's not low enough. You see the level is how high with the Blackpool Tower. So the relationship between the tower and Dow Craig in the back of the mountain would be as expected because you're seeing it at a level height. So the angular size would be as it should be. Now if you had to change his elevation to the correct elevation, which would practically put the camera inside the ground, which he wouldn't be able to do, and he has to change the aperture diameter of his lens, which would have to be much smaller in conjunction to keep it with the ratio of the actual observation, which is impossible, then you would only be able to actually mimic the actual demonstration properly. So what all I'm trying to demonstrate here is, yes, he did it to scale, brilliant, but just because of the observation angle alone, it shows that you cannot really do it to scale. So it's all just optical in the end of the day. Then I got the one underneath that with the differences in the observer's angle.
Yep.
Okay, yeah, it's showing the difference with the eye level. Can you see how the eye level to Blackpool Tower is on the actual observation compared to his demonstration? No, it's just software. Can you see the Blackpool actual photo? You're looking up at Blackpool Tower because of the eye level.
Yeah.
Where compared to Bearded's, you're looking straight at it. You are at a much higher elevation.
Yeah.
So that changes the relationships with the occultation. So that's why, again, observer's angle is very important when it comes to observations.
I told him to try and keep the line in the centre. That's what people want.
Yeah.
Get that line right in the centre of the camera.
But it's amazing how just the angle towards the observation changes everything. I mean, that's why I said if you could do it with the drone that you wanted to do, and go with the drone higher, you would see how Blackpool Tower would become smaller and the mountains in the back would grow. You'd see that because the angle, you're pushing that limited angle further, and the problem people have on this photo with Blackpool, you can't see the compression from the base of the mountain because Blackpool itself is occulting in front of that base of the mountain. So this so-called drop they associating is literally just occulted by Blackpool Tower because the mountain is compressed in the distance due to the viewer's angle.
Yeah.
And then I got the last slide, the one just underneath that one.
Difference is in the observer.
The different, yeah. And it's just me comparing again, to show you the bit of poles when they put level to each other. The ones with the lower angle looking up, and the one is level looking level at it. If you can see the lines, how it's compressed and had an optical drop on the right just because the viewing angle is you're looking up, whereas on the left you're looking straight out as his demonstration, and thus it has the what you would expect to see if you've done the trigonometry on a flat surface, because that's literally like you're just looking at it at a single angle. Well, I think that's the presentation. Yeah.
I like it. The angle.
Yeah.
Yeah.
So at the end of the day, what we realize is everything you see on the photo is optical. And if you're going to make claims on it with trigonometry, you can't really stake a claim on it, because it's optical and it's just a picture at the end of the day. One thing it does show, though, doesn't matter with the viewer's angle, is the claim is the set radius, and it goes much, much further than that set radius. What it does show as well is you can only have this on a horizontal plane. That's my point. Observer's angle destroys Ranti's argument.
I like it.
Any questions?